Okay, we're going to be starting on the next section of the course, and this one is called the slope deflection method. So there's some things that we need to talk about, or some terms that we need to define here. Well, firstly, you use the slope deflection method when you wish to calculate a statically indeterminate structure. So we can see here a statically determinate structure where you can work out the forces just by inspection, and by adding another span, or perhaps by making that n into a fixed instead, you've suddenly got a statically indeterminate structure. So the slope deflection method was probably one of the earliest well-used methods for calculating such statically indeterminate structures. And it was later replaced by another method which is called moment distribution, which Gary Raftery will be teaching you in the third year. Basically, this one is an algebraic process, whereas the moment distribution method, it requires is more of an iterative process. So you just use iteration, a bit like Simpson's rule or something, to more or less get the same answers. So the concepts are pretty similar, and if you can grasp this one, then what Gary will teach you in year 3 would be quite straightforward. So we're going to be introducing some terms. So one of them is FEM, and FEM stands for fixed end moment. Fixed end moment. So that's one of the things that I would need to explain. There's another word which is called reactant, reactant solution, and there's another one which is called the active, I just call it active solution, but I may use a different term later on. So active solution is basically when you've got when each end is simply supported. So as a case here, this is an example of a statically indeterminate structure. So this one is statically indeterminate by 1, because you're adding one extra unknown, which would be the vertical reaction here, compared to this one here, which is statically determinate. So the 1 signifies that you're adding on one extra unknown, which therefore needs to be calculated. So just as an example, I call that A, I call that B, and I call that C. Then the active bending moment for AB, which I'll draw like that. The active bending moment is just one end pinned, one end roller with the same load acting there. So that would be the active bending moment. And on this side of the span, we'll just say that's B. And then that would go on to become C, and there's no load, and so the active solution is 0. So we'll talk about these a bit later on, once I've defined some terminology or defined some notation. So let's move on. So remember, fixed end moment, reactant solution, and active solution, and an active solution for any span of a, maybe you've got a 3 span, 4 span, each span simply supported, and you'll be able to work out what's known as the active solution. All right, so let's move on. So let's ignore this for the time being, but this is called the general case, and we'll try and explain this table here, which engineers can, well, fixed end moments here, which engineers can would have on the desktops, and basically be able to look up these values. So where does the fixed end moments come in? Before we go on, I should add that we now, at this stage, we need a sign convention. And the sign convention that you need to remember is that clockwise is positive. So I've gone to quite a lot of effort before not to mention sign convention when it comes to bending moment, I've always been using the terms hogging and sagging. So I've never introduced whether something is positive or negative, and I've said you're at liberty to call hogging positive or call hogging negative, whatever you want, and just plot everything on the tension side. When we come on to this slope deflection method, we do need a sign convention. And so, as I said, the sign convention is clockwise is positive. So this is called a special case. So if we flick through to the previous page, we will see a beam where you can put the point load at any position. It doesn't need to be at the center. So, but for the specific case of it being in the center, or halfway along the beam, which you can get through here by having alpha as a half. So if alpha is a half, then the load is at the center, and you put half in for alpha in these, and you'll end up with minus negative 1/8. And you put alpha as half on this side here, and you will also end up with 1/8. So that's just why the special case is for special cases, or more, should I say, common cases, where you've got simply supported, when you've got a point load in the center, you've got a UDL, you've got a UDL on one part of the span. Now, if we've got a case like that, so I've got the beam here, which I'll use as an example. Let's look it up here. So here is one end fixed, and one end is also fixed. Technically speaking, it should also be on a roller, so you don't get the chain effect or the catenary reaction effect. If you don't know what catenary reaction is or chain, just Google and you'll see that it's when that end's fixed in it. It provides some extra other restraint which we don't want to include. So you'll see it like that, but what it really means is that it's free to move in that direction here, but not free to move in the other directions. So if we put a point load right here at the center, we can see what the deformed shape would look like. And hopefully you can see on this side here, that the reactant solution, or the moment reaction at this end here, is going to be in the clockwise direction. Okay. So let's just focus on that side to start with. So I'll draw it up here. I'll just draw it up here, and then we've got both ends fixed, and then we've got the other end fixed, and then we've got a load in the center there, and that would want to go like that. So we would therefore know that the reaction at the end is going to be in that direction there. Okay, and we can see that this is a clockwise. This is a clockwise moment. Remember, I said clockwise is positive. So if this load is called W, this is how to use it. If this load is called W, if both ends were fixed in, then we'll be able to work out the reaction or the moment reactions at the two sides here using this table. And it's called fixed end moments because we're assuming both ends of the beam are fixed. So if both ends of the beam are fixed, there's a special terminology that would describe the reaction moments that are generated on both sides, and these are termed fixed end moments. So let's see how to use the table. All fixed end moments, formula times total load times span. So we've got W is the total load, the span is L, so the span is L, W is the total load, and the formula in this case here is 1/8. So here we've got 1/8, and that would be multiplied by the total load, in which case would be W, and the span L. Okay. So we've got load of W, so reaction there of course W/2, and then the fixed end moment on the right hand side is 1 over 8 W times L. Okay, so that's how to interpret that table. Now we look at the other side, and remember we've now got a convention which is clockwise is positive. So I'm going to draw the reaction here, and I'm going to draw the reaction in a clockwise direction. So if that's clockwise, clockwise would be also acting in that direction there. Now we know from this case here, where both ends here are fixed and you've stuck a load down in the center, that the bending moment or the reaction moment is going to be acting in the anti-clockwise direction. So all the Zora-Q stuff and all the stuff we talked about before tells you that the reaction moment and the bending moment at this point here is going to give rise to an anti-clockwise moment. But now we've got a sign convention that we need to follow, and the sign convention is clockwise is positive. Okay? So using the clockwise is positive, we've got to draw it like there, and then we've got the formula, which is this time minus 1 over 8. Okay, the minus is not clear. So the formula is minus 1 over 8 multiplied by the total load W multiplied by the span, which is L. Okay, so that's how to interpret the special case. So another case would be when you've got a UDL acting on the beam here. So let's try and draw it like there, and then this time here is got a UDL, and the UDL would be maybe small w per L, and over the total length it would be W total as they've got there. Now if again we've got the beam and both ends are fixed in, so we're going to be calculating the fixed end moments. So both ends are fixed in, so my fingers are going to try to approximate a UDL, so you can see the deformed shape here. Okay, and we can again see that the reaction moment at one side, at the right hand side, is going to be in the clockwise direction, which we'll show like there. And then this equation here then becomes 1 over 12 multiplied by formula, which is 1 over 12 times the total load, which is going to be W, and then multiplied by the span, so you're going to get 1 over 12 WL. And then on the other side we would have a reaction moment shown like there, and then the reaction moment is also, because clockwise is positive, I'm going to have to put the clockwise arrow here on that side there, so to show a clockwise, but we're going to have to put a negative sign in front of it, and it's going to be negative 1 over 12 WL. Okay. So this is how to use the table, and the table basically just helps you look up what a fixed end moment would be for a different situation. So, okay. So if we had to draw the bending moment diagram for this case here, so I would draw the bending moment diagram to be like, I would draw the bending moment diagram to be like that for that case there. And then if I had to draw the bending moment diagram for this case here, I would draw it like there. Okay, just draw it like there. And then let's look at this side here. So remember, the bending moment at that point there would be acting in that direction there, which would be in the same direction here. But this one here, well, we know that it would be acting in that direction there, but we've got to show the arrow as clockwise positive. So I would then show it also in the clockwise direction, and then we know that we'll be using the negative sign. So you'll be quite happy with that one, since the arrows are in the right direction. But in this side here, we'll now have to use a negative sign to pre-assume that all the moments and stuff clockwise is positive. And of course at the end, when we come to reinterpret what this is, if you've got a negative sign and an arrow hit there, you're at free liberty to remove the negative and to switch the sign and to switch the direction of the arrow. Anyway, this is what's known as fixed end moments, and we'll be talking about these later on. So some more pages here. Just describe beam deformations. Now, the slope deflection equation, this is the proof of the slope deflection equation, so it's there for you to read if you wish to, but I'm not going to be testing you on the derivation, okay? So you don't need to know how to derive it, you just need to know how to use it. So another bit which we can do is, I'm not going to be talking about deflections or settlement, so like if you have a foundation or a house or a bridge and one of the foundations is settling, then the settlement would lead to a fixed end moment. So the settlement would lead to a fixed end moment, and if we go further here, no, there's no example of the settlement, so let's leave that. All right. So that means that since I'm going to be excluding settlements from this part, that means that that bit of the equation can be removed. Okay. Incidentally, the derivation comes from moment area, which you've studied before with Quincy and Lucas. So let's now interpret what this means here. In terms of, well, at least what the equations mean. Firstly, when you see this F here and the F here, that means that we're talking about the fixed end moments. So whenever you see an F, that means you're talking about a fixed end moment. MAB and MBA are the actual bending moments. So if we go back here, for example, we've got this case here, so I would be drawing a bending moment diagram like there, okay, and then I would be maybe sticking an arrow there and sticking another arrow there, okay, to represent the hogging, and of course that one there is 0 and that one there is 0. So this is the bending moment, of course, because this is the bending moment diagram, and the magnitude of that one, or how we're going to call the notation, I will call that MAB. All right. So sorry about that. I'll call it MBA, because it's MB looking at A. So that arrow is called MBA, and this is the bending moment. And on the other side, I've got MBC. Okay. So let's, for example, say that the bending moment at point B is 100 kilonewton meters hogging. Therefore, MBA would be 100 kilonewton meters acting in the clockwise direction, and MBC would be 100 kilonewton meters acting in the anti-clockwise direction. So you can see why we sort of need to introduce signs at this stage if we're going to be solving anything. Now, with the slope deflection equations, each span of the beam, so this beam has two spans, AB and BC, so each span of the beam has two equations, and we can write those two equations out, and then so from this one here, two equations, here two equations, so 4 equations in total, and 4 equations in total can be solved, as we'll show, using simultaneous equations. and then out at the end you would be able to solve MBA and MBC. So hopefully that explains what this notation means. So for any span, the equation of course would be given to you in the exam, but for any span, this is the bending moment AB, which is actually the bending moment, say, at that point there, in this example which we'll go through. The fixed end moments we'll be calculating, as you've seen, and it's going to be equal to 2 times EI, where EI is the bending stiffness of the beam, divided by L. Sometimes in the examples, one beam would have twice the bending stiffness than the other beam, but in this case here, in most cases here, you would say uniform EI, i.e. that span and that span are both from the same bit of steel and of the same cross section. Then we have 2 theta AB. So let me just draw it a simply supported beam here. So I'll draw it a simply supported beam here, and I'll call that A, and I'll call that B. And this is where the name comes from, the slope deflection equation. So we've got simply supported beam, and then let's say that is going to deform like that under the point load. We can see that there's a slope or gradient here, so it would be that angle that you are measuring with a protractor or something. So there's that angle there, and then on the other side of the simply supported beam there would be another angle there. Okay, so this angle is going to be called theta AB, because it's A looking at B, and then this angle here is going to be called theta BA. And if you remember, we talked about signage before, so clockwise is positive, so this one has rotated, has a rotation in the clockwise direction, and so if that and that are equal magnitude, this one has rotated in the anti-clockwise direction. Okay, so hope I've got that right. So we're going to have to when you do the calculations and it comes out in the wash, if your answer is positive, that means that the rotation is in the clockwise direction, and if your rotation is negative, that means the rotation is in the anti-clockwise direction. Okay. So let's get on to an example. So this one here is an example of a 2-span continuous beam. So for a 2-span continuous beam, the left hand side is fixed, the right hand side is also fixed, and we've got a roller acting, or support acting at the center. So that would be how I would want to show it. Now look at what happens here. So we've got 100 kilonewtons acting downwards. So there's 100 kilonewtons, and we can see. Let me get this right. So if you look at that, as I apply the 100 kilonewtons, so as I apply the 100 kilonewtons, you can see that that one has rotated in the anti-clockwise direction, and this one here, 100 kilonewtons on this side here, or 10 kilonewton per, has caused a clockwise rotation. So originally it would have been, well, originally it's here, and now it's rotated in the clockwise direction, okay, which you can see there. All right. So under this load, so if both sides, of course, had exactly the same load, so if that one had been 100 and that had been 100 as a point load acting at the center, then there would be no rotation at the center, at the support there. But because that's not symmetrical, it's going to rotate. It's either going to rotate in that direction or it's going to rotate in that direction there. So jumping through to the solution, which would be on the next page, we can probably see that the rotation is going to be in the anti-clockwise direction, and I think that could be anticipated. So that means that when we solve this problem, we'll find that the center has rotated in the anti-clock. We'll see that there's been a rotation in the anti-clockwise direction, just like that. Okay. And that's because this load is more evenly spread out over this part of the beam. So in other words, having the 100 kilonewtons as a central point load would lead to more rotation, would lead that one to be stronger, sort of bigger, causing a rotation in the anti-clockwise direction at that point at B. Okay. So when we've got more spans, as we've seen here, we've got A, B, C. We've got to sort out some sort of notation, and we've got to sort out some form of notation for the B and C part, as we'll see. So now with the slope deflection method, the first thing to do is to work out what the fixed end moments are. So in this case here, we've got 100, so we keep the same span, which would be AB, and we keep the same load. So important thing when you work out the fixed end moment is you keep the same load when you work out the fixed end moment. So if there's no load acting on the span here, then the fixed end moments are of course 0. So we've got a span of 10, and then we've got a load which has been applied in the center, 5 halfway down here. So what we'll do is we'll imagine that you've got your 10 here, but imagine that both ends are now fixed, and this is AB, and this one here is now AB. So you've got your 100 kilonewtons acting on the system here, and on span AB, if we say we're going to fix both sides, so that side is fixed and that side is fixed, that means this side has no rotation and this side here also has no rotation, and the load is coming down the same. We are able to look up that table and we can get the fixed end. We can get the fixed end moment. So I've put it down with my finger there, and you can see both sides are have come out at 90 degrees, or there's been no rotation at A or B, and some moment has been generated. So let's go through the calculation. So the first thing to do is remember that the sign convention, and the sign convention is clockwise is positive. So we draw these arrows, which is the bending moment, or is also the reaction, because they're the same thing, and they're drawn in the they're drawn in the clockwise direction. So you can see that one is clockwise, and that one there is clockwise there. So this is MFAB, where F stands for the fixed end moment, and this is MFBA, where F also stands for the fixed end moment. And it's a very, very mechanical process. You just go back to the table that you have, and on the table here, if you remember for the special case here, we've got the load acting in the center. L is going to be equal to 10. So MFAB is going to be equal to negative 1/8 multiplied by 100, which is the load acting downwards. So formula, negative minus 1/8, because clockwise is positive, times total load, which is 100, multiplied by the span, which is 10. So we can see that we've calculated the fixed end moment, and that's come out as negative 125 kilonewton meters. Now there's another fixed end moment on the other side, and again we use the same equation. So draw the clockwise arrow, which is also clockwise for the moment reaction. So that and that are the same. And MFBA, in this case here, MFBA is going to be equal to positive total load times L, which is 110, divided by 8, and we're going to get 125. So by virtue of the symmetry, you didn't actually have to calculate it out. It would just have been the opposite of the other one. Okay, right, so that explains how to get the fixed end moments. Now we've got this other span here, which is BC. So you take this one here, and then this one is BC with the UDL acting on it. So this now represents span BC. So that one had, the original span BC had a UDL acting in it, so the fixed end moments case would also have the UDL acting on it. So this is span BC. So that again we end up with, so I'm just trying to use my fingers, that again we end up with some sort of deformed shape, and we get some fixed end moments which we can also calculate. So we have M fixed BC. And this case here, again going back there, we get the minus 1/12, which we see there, times, in this case here, it's the total load is 10 times 10, or small w of 10 kilonewtons per meter multiplied by length to give you the total load multiplied by length. So here just note that's total load. So formula, minus 1/12, total load 10 times 10 multiplied by the span, which is 10. Okay, so if you punch that through the calculator, you'll get that as minus 83.3. And if we did the same for the fixed end moment on the other side, which would be MFCB, it would be the opposite, or the opposite sign. So it would be positive 83.3. Now let's look at the geometry of the problem. So in the geometry, let's just make some observations based on how this deforms. So remember, we call this A, we call this B, and we call this C. Now this is the span AB, and under the load there we can see that that one there is going to have no rotation. So in the case of a fixed support, theta AB is going to be equal to 0. So when one end is a pin, there is a rotation, but in this case here, that being a cantilevered end or a fixed end, there's going to be no rotation. So from the geometry, we see theta AB is equal to 0, or the rotation at that point under this system of loads, of course, or this, or because of the beam itself, there's going to be no rotation at that point. We can also see that at A, there's going to be no deflection. So the deflection at A is also going to be 0. Now the deflection at B is also going to be 0 because that is a roller. So it can't move up and down, but it can move sideways. But the vertical deflection is going to be 0. Okay? So no deflection at that point there. Point C, which is this one here, again we can see there's going to be no deflection in the up or down direction. So delta C is going to be equal to 0, and because it's fixed, when it deforms under the load, we can see that whatever angle it was is going to remain at that angle. So that's just by inspection of the system. So we can make some observations about the geometry. Now maybe here, maybe here I would just draw that one. And then maybe here I might draw that one there, and then let's just call that A, let's call that B, let's call that B, and then let's call that C. So that represents that case there. Now we can see that, going back here, whatever rotation there is on both, so the rotation either could be 0 or it could rotate in that direction, which would be clockwise, which would be an anti-clockwise rotation on both sides. So here you can see that side's theta BA has gone in the anti-clockwise direction, and you can also see that theta BC has also gone in the anti-clockwise direction. So when we say that there would be a rotation at B, the rotation on this side would be called theta BA, and the rotation on this side here would be called theta BC. But when we solve it, we would find that theta BA must be equal to theta BC, which we could just call theta B. Okay. So that's so whether it's a clockwise rotation or an anti-clockwise rotation, we would expect by compatibility at that point that there would be a constant gradient on both sides, and therefore this relationship would always hold. Okay. In other words, there's not going to be a kink, or in other words, both the beam is acting, the two-span beam is acting as a system, right? So that's going to be your theta B. We can also make another observation. Going back to this case here, let's say that we have to, so we could probably already predict that there's going to be a hogging bending moment under B. So at B, this is just a prediction for this particular case, there's going to be a hogging bending moment. So the hogging bending moment would look like that, as we know. And just for argument's sake, let's put the two arrows there. Now this side here, well, we know that the magnitude must be the same on both sides. So we'll call that MBA, and we'll call that side MBC. Okay. Now let's say that clockwise is positive. So in this case here, that one is going to be in the anti-clockwise direction, and this one here is in the clockwise direction. So what I'll do is I'll put a negative sign. I'll put a negative sign there, and then I would maybe just switch that there. Okay, and might be easier to say minus MBC. So this would represent hogging, and as I said, put the arrow on the side, you can get rid of the negative sign. So the relationship which we could say is that, let's say that MBA is, say, the magnitude of BA is 100, and the magnitude of BC must also be 100. So we could say MBA plus MBC must be equal to 0. Right. Now MBA, we'll say that's 100, and then MBC must be negative 100 according to here, and we can see that that must be equal to 0. And if you did the reverse, and if you said there could be a sagging moment at that stage, at that point there, and call that MBA, and then call that MBC, change the arrow to obey your sign convention, and then say that's negative MBA, and then the same thing would hold out. MBA plus MBC, the magnitude would be the same, they would need to be the same. You add them together and you're going to end up with 0 as well. So that also holds. MBA plus MBC is going to be equal to 0. Okay, so these are some observations. The bending moment on either side. Remember I said when we calculate these, when we interpreted these, I said these MAB and MBA are the bending moments. So the bending moment must be equal and opposite on both sides here, and the rotation must be the same on both sides, okay, as we've demonstrated here. So let's move on to writing up the equation. So write out the slope deflection equations for the ends supported. So we've got two ends, we've got two spans, AB and BC, and both spans, each span has two equations. So the first one is simple. MAB minus M fixed AB minus M fixed AB, and we can see M fixed AB minus two negatives make a plus, so plus 125 is equal to 2EI over L2 times theta AB, which is 2 times that rotation. That rotation is 0, so we look, there's 0 there, plus theta BA, and we can call theta BA just theta B. Because of compatibility, the rotation on both sides of B have to be in the same direction. So we can simplify it and just call it theta B for both sides. Plus theta B, and this bit of the equation we ignore because I don't want to cover settlement. Second equation, MBA. So MBA here minus M fixed BA. So the fixed for the BA is going to be 125, so minus 125 is equal to 2EI over L, where L is 10, 2 times theta B plus 0, because theta A is 0. Okay? So that's the second equation for this one here. Now we'll repeat the equation for span BC. So for span BC, MBC plus 83.3, because minus and minus make the plus, is equal to 2EI over 10, 2 times theta B plus 0 plus 0. And the last equation, MCB minus MFBC. FBC is 83.3, so minus 83.3 is equal to 2EI over L, which is 10, and that's going to be equal to 0 for the CB, because there we've said CB is equal to 0, so theta CB is going to be equal to 0 plus 1 of theta on the other side, which is going to be theta B. So we now say the middle equations can be added together, the ones that talk about the equilibrium at that point there, because the bending moment has to be the same on both sides. So the equilibrium equation, whether it's hogging or sagging, is MBA plus MBC must be equal to 0. So we're not presuming it's hogging or sagging, we're just saying whether it's hogging or sagging, if you add the bending moment on both sides by equilibrium, it's going to end up to have to be 0. So we have adding these two equations together, which would get that. So add the two equations using the equilibrium MBA plus MBC is going to be equal to 0. So if you add these two together, MBA plus MBC, 0, so that one and that term get rid of, minus 125 plus 83.3 leaves you negative 41.7 is equal to 2EI over 10, so we keep the 2EIs over 10, and here we're adding theta b's, so you end up 2 theta b plus 2 theta b is equal to 4 theta b. Substitute from there, you can work out what theta b is. Theta b is just minus 41.7 times 10 divided by 2EI over 4. Okay, so we've got a value for theta b. Now, having a value for theta b, we can now solve MAB, we can solve MBA, we can solve MBC, we can solve MCB, and we can work out what each of these are. So rationalize. This is what's known as the reactant bending moment diagram. So this is known as the reactant bending moment diagram. So you can see you can see what the values are. So first thing is maybe you draw out your span there. So that would be your, let's just call that B, and that would call that A, and we would call that C. And we've worked out what the bending moments are. Now let's just draw our semicircles for each side. Okay, let's draw our semicircles for each side. And just for now, let's say it's going to be clockwise. Clockwise is positive, so clockwise, 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 clockwise. So that obeys our sign convention of clockwise is positive. Now, MBA is, so I don't think we need the A, B's and C's, so I'll get rid of them, and I'll just call that MAB, and then I'll call that MBA, and then I'll call that MBC, and then I'll call that MCB. Right? So MBA is negative 135.4. So that means it's acting in the anti-clockwise direction, and it's going to be 135.4. MBA is positive, so it's in the clockwise direction. So because it's positive, I can write 104.2. And for this one here, MCB, it's 72.9, and again it's positive, so I can draw that, okay, with 72.9. So basically that one and that one were positive and that one was negative, so I've got to change that one there. Now if you remember, you don't need to do this, but because you could probably immediately draw that, because hogging needs to be with the arrows on that side there, but if you want it to be pedantic about it, you could see MBA plus MBC is equal to 0, so that needs to be on the negative side, so put the negative side, that means that arrow has to be reversed, so it's 104.2. So this leads rise to what's known as the reactant solution. So if I now draw this one here, so you can do it on a bit of graph paper, so that would be 135.4. So that would be 1.135.4, and that one there would be 104, and that one would be 72. And then I could draw a dotted line. Oops. Then I'll draw a dotted line between there and there, okay? And this is what's known as the reactant bending moment diagram. Now, to the reactant bending moment diagram, you need to add on the active bending moment diagram. So when we talked at this, which is just theory of superposition, so when we talked at the start, I said we can work out an active bending moment diagram for each one. So the active bending moment diagram for the first span, which would be AB, that would just be something like that. And then the active bending moment diagram for the second span, BC, would be something like that. Okay. And then we'd be able to say that value there is PL over 4, or the load, so 100. So that distance there is going to be 100 times L divided by 4. And that one there would be WL squared over 8. So the bending moment would be 10 would be W L squared times 10 squared divided by 8. So that's just the maximum value for a beam under a UDL. So this is known as the reactant bending moment diagram, and this is known as the active bending moment diagram. The active is just pretend each end is simply supported, and the two need to be added together. So let's add these two together. So that value here is 135.4 plus 0, because that's 0 there, and that value would be 135.4. 135.4. That value is 104.2, so that one plus 0, so that would also be 104.2. That value is 0, and that value is 72.9, so that would go up to 72.9. Now, what happens at the middle? So this is 104.2, and this is 72.9. So we need to know what that value is. So that value is just going to be the average of 135.4 and 104.2. So let's do calc. So the average of 135.4 plus 104.2 is equal to 119, so that value is 119.8. And PL over 4 is 100 times L divided by 4, which is 250. So this is hogging because it's above the line. Let's just draw a double line there. And then this is sagging because it's below the line. So 119.8 minus 250 is going to give me 130. So that value goes down as negative as 130 there. All right. So that's 135.4 hogging, and this value is 130 sagging. All right. And then that portion plus that would just be going up like there, and then this again would end up something like that. So again, to find that point there, okay, we'll need to take the average of those two. So the average of 104.2 plus 72.9 equals divide by 2, and you're going to get 88.5. So that value there, the average of those 2 points would be 88.55. And then WL squared over 8, that is going to work out to be 125. So 88.55 hogging minus 125 sagging would give 88.55 minus 125, and that's going to give a value of 36. So that would be value of 36. So that's where you get the bending moment diagram. So we've used the slope deflection method to get the reactant moments, which would that value, and that value, and then we add it onto the active bending moment, which is just the simply supported beam for each span, and then we can draw out what the final the final bending moment is. So that's the solution of how you can easily solve a statically determinate problem. Now let's have a look at the drop box. Okay. So generally with these problems you can solve them on 1 or 2 pages of A4. So I've got an example here that a student wrote out for me, so you can see that there, and she's written out the solution in 2 pages, and what she's done beyond that is once you've got the bending moment diagram, from there you can work out what the reactions are, and then once you've worked out what the reactions are, you can get the shear force diagram, or you could calculate the reactions and then you can draw the shear force diagram, and then from the shear force diagram, from the bending moment diagram you can go to the shear force diagram, and then from the shear force diagram you can work out the reactions. So she's written out this solution here, which is 2 pages, which would eventually conclude with what the reactions are. All right. So a much longer solution. So I got a student to write this out for me before. So it goes on to quite a few pages, but it just goes through the steps that we've just covered, stepping out the problem, working out the fixed end moments, what the active bending moment diagrams are, which you can see they worked out the fixed end moments, where all the numbers come from, the slope deflection equations, everything that we've gone through, adding them together, solving the slope deflection equations, but basically giving all the detail that you might feel that you might need the first time you look through it, and then drawing the bending moment diagram, which you can see here, adding the active adding the reactant and the active to get the actual bending moment diagram of the shape of the system here, of the two-span beam system here. So finding the reactions from here, just using statics, and then going through how to solve the reactions. So that one is also there. I've also got a solution, which is that one there. So I've got a printout of this here, so I'll just flick that through. I've also got 2 videos. So these are videos that I've cut out from previous years where I actually had the benefit of the document camera at the university. So if you feel what I've done is not that clear, you can watch these 2 videos, which would basically just show the same thing. And then the final thing is that I've got a written out solution, which I'll show here now. So here's the solution: 2-span continuous beam. Find the bending moment, shear force diagram, and deflector shape. 2-span beam. So as we've been through it, here are the calculations to work out the fixed end moments for AB and BC. The geometry, then, as we've defined, these are the points of contraflexion, by the way. Write out the equations. So here are the slope deflection, the 4 slope deflection equations, adding them to, and this time there's a bit more detail, or it shows a bit more detail as to how the theta b's are substituted, if you need to see them, and how each of the MBAs, MBA, MCBs and MCBs can be calculated, which you can see here. And then active bending moment, which we can with the 250, the 125, and then the final bending moment diagram again, which is the sum of the active and the reactive bending moment diagrams. So from there, I then same problem, but we've now calculated using slope deflection whether the bending moment is hugging or sagging, and in all cases here we've worked out A is a hugging moment, B is a hugging moment, and C is a hugging bending moment. So draw the reactions of ABC, which we've done up there, and then I've done span AB first. So I've taken out AB first, and so you could take moments, so that represents span AB with the bending moments there, and what we're looking for is to calculate the shear force. So take moments about A, and that would give rise to what that value is, which tells you that that's 46.88, or you can take moments there if you wish, and that would work out that as being 53.12. So you've got 2 choices, and obviously the sum of these ones has to equal the 100. Then you can do the same one on the other side, which would be span BC with the load going down. So again, we know what these are, because these are the reactant bending moments, and then the loads are UDL, so you can take moments about B, and that would give you SCB, and then you could take moments at C, and that would give you SBC. So you can see the calculation laid out here to get these, and then from there you could then transplant that onto a shear force diagram. So we would work out that SAB, which would be that value there, is 46.88. So SAB, maybe there's a mistake there. Yeah, no, SAB is 53.12. Sorry, I was looking at the wrong one. 53.12, and that's a 53.12, which is either the shear force a hair's breadth away to the right, or it's the reaction. So you can see that written there. Shear force up, which we can see there, down by 100, then goes up and goes back to 0. And then for the second span, which would be span BC, we would see the shear force is 53 0.12. So SBC would be from there to there, which is 53.12. And then the total reaction at B, which would be that value there, would be that value of the shear force to the left, plus that value of the shear force to the right, and that will give you your 100 kilonewtons. And then back to the other side, we've worked out what the SCB is on this side here, and that's also just the reaction at C, which you could calculate to be 46.88 or 46.88. So you can see that all drawn there. Then here, which would be the final page, here you've got the original problem with your reactions that have now been solved. You can see down here the bending moment diagram that's been drawn. You can see the reactant solution there, and then this is just added onto the active case to give the final bending moment diagram. And the active case simply supported for AB with the PL over 4 to work at the maximum bending moment, or the WL squared over 8 on this side here, and you can see all the additions that have gone there to generate the final shape. And then here the final bit is just check the bending moment values and just make sure that they all come out okay. So this would be the a fully worked out solution for that. But of course, you know, if you get this question in the exam, I would expect that you would be able to show it if you wanted in 2 pages. So you could, or on 2 sheets of A4. So you could look at, so again, if you can follow it, sorry, I've got it, so this one here would have solved this whole problem, worked out the reactions and the shear force diagrams and everything in 2 pages. But if you wanted more detail, then more detail is given there. And if not, I've also, as I said, I've also stuck up 2 videos there of me going it through under the document camera 2 years ago. So that's all for now. And the next question that we'll look at would be a three span beam, and I'll go through it, but there's also a longer solution which you'll be able to see there. So hopefully we'll be doing this one when we get back to the uni.